Hi, my name is Hirat. I'm a PhD candidate at the University of Michigan, advised by Ronald Brzezinski. I'll be presenting a work done in collaboration with Facebook and University of Michigan about improving performance of flash-based key value stores using storage class memories as volatile memory extension. With all the applications we're using from Facebook, such as WhatsApp, Instagram, and so on, Facebook's overall data is growing, and videos and images are uploaded every second. And all of these applications, such as loading content in an app, are latency sensitive that needs to be accessed fast by users. And flash-based databases are used to provide the demand. As the size of the data increases, from capacity perspective, we will require more memory. Key value stores are one of the largest storage services deployed at Facebook in flash-based servers. And as the data grows in key value stores, we can use multiple small servers that enable scale-out solutions by sharding databases and using multiple servers per service, or we can use large servers that has more memory per server. Now let's look at the architecture of the small and large servers. We have two main Facebook storage servers. One is a server with 2 CPU and 256 GB of memory and SSD storage, which we call 2P server. The other one is with 1 CPU and 64 GB of DRAM and SSD storage, and this is the 1P server. Both servers have their pros and cons. For 2P servers, we get high performance per node, but it's expensive. And for 1P servers, it's cost effective, but it has lower performance per node. Lots of workloads benefit from 1P servers without their performance getting affected. But key value store workloads use DRAM as cache. So in 2P servers, we'll get high DRAM hit and less I/O utilization, hence data access latency will be fast. But when we go to 1P servers, we will have lots of DRAM misses because of the small DRAM size, and hence increasing access latency. Another option that we explore in this paper is, can we use storage class memories to create high performance and cost-effective servers? Let's first see what storage class memories are. Storage class memories have both the characteristics of memory and storage. They are byte addressable and can have large density than DRAM per module. If we look at the memory hierarchy, they're in between DRAM and SSD. They have lower bandwidths and higher access latency than DRAM, but they're much more faster than flash and can be used to extend the capacity of 1P servers beyond what we can do with DRAM. One such storage class memory commercially available is Intel Optane memory. Intel Optane memory comes in DIMM module and is byte addressable over DDR2 bus. In its current form, it comes in a much higher capacity than DRAM, up to 512 GB per module. Intel Optane memory has two operation modes. Memory mode, where DRAM is a direct map cache of Optane memory, or app direct mode, where we can control where we place data between DRAM and Optane memory. Our goal here is to use DCPMM to create new server variants and to evaluate if we can mitigate the performance loss of reduced DRAM in 1P servers. This way, we will have highly accessed data in DRAM and cold data in SCM. And then we get high hit to both SCM and DRAM data, and we will reduce I/O utilization, reducing overall data access latency and increasing performance. Our work focused on RocksDB. RocksDB is a key value store developed by Facebook and used by many other companies. At Facebook, it's widely deployed for various storage workloads. RocksDB uses memory for meme table, which is used for write, and block cache used for fast read access. Key value pairs are organized in stored string table files and are stored in SSD. In our studies, we first analyzed deployed RocksDB workload, and we found out two things. The first is the largest memory consumption comes from block cache in 2P servers, and the other is we learned read passes are critical and optimizing reads will give us high performance. Therefore, we focused on read-dominated workloads in this work. We chose 3 read-dominated RocksDB workloads for our studies. The workloads are WhatsApp, which is a messaging app based on RocksDB, Tectonic metadata that holds the metadata for large blob storage services, also based on RocksDB, and Laser, a high throughput service used to read from Facebook's real-time data aggregation services. And then we study the characteristics. As we discussed earlier, all workloads have more reads than writes, as seen in this graph. We then study the temporal localities in the workloads. We learned that we have power law characteristics in the key access. In the graph on the right, we can see that loads of the key access come from few of the keys. This clearly shows that we have hot blocks that are accessed more frequently and colder blocks that are accessed less. Given this information, we analyze two things. The first is using memory mode that does not give us control of caching capability of DRAM, and the second is using UpDirect mode and naively implementing block cache in SCM. And then we compared it to our work, which is based on our optimized UpDirect mode using temporal locality to place blocks between DRAM and SCM, where we place hot blocks in DRAM and cold blocks in SCM. In this figure, x-axis shows the size of DRAM and SCM in the system we evaluated. And in the y, we have relative throughput of optimized UpDirect mode to memory mode in each systems. Here, higher is better. So as we see in the graph, for RocksDB, having control of caching of data between DRAM and SCM gives up to 60% more throughput than memory mode, which does not give us any control of where we place data. And in this figure, we have relative throughput of naive SCM block cache versus our implementation. And as we see here, optimized UpDirect mode gives better performance in all cases. So we focused on UpDirect mode and careful managed caching. So based on the implementation of RocksDB, we extended to build a hybrid cache with large block cache extension using Optane memory as volatile memory. Then based on locality, we placed hot blocks in DRAM and cold blocks in SCM by managing and transferring blocks between DRAM and SCM. We then use libmemkind library, which is a library used to allocate data to different memories in RocksDB. Now let's see the details of hybrid cache. A hybrid cache is a new top-level module that handles multiple cache in hierarchy. The internal components are first, list of block cache. So here we only have DRAM and SCM cache, but the module can handle multiple caches. And with changing configurations, we can have memory allocation to more memories than DRAM and SCM. So for example, for DRAM NUMA node, Optane SSD, and so on. We then have cache admission policies that says policies of where to look up data first, how to insert data, and how to evict data. And finally, we have operation management that redirects DB operation to different caches based on cache admission policies. Now let's look closer to how data is managed with admission policies. For example, one cache admission policy is DRAM first. In DRAM first admission policy, new blocks are first inserted in DRAM and are read from DRAM after that. And as time goes on, RocksDB tracks list recently used blocks in the LRU list based on this recently used policy. Then when DRAM is full, the list recently used blocks are considered as cold blocks and they're moved to SCM cache. Similarly, when SCM is full, LRU blocks are evicted. And then during lookup, we will look both DRAM and SCM until the data is found. We can also create multiple admission policies, and we evaluated and compare most policies in the paper. And DRAM first was the best policy. Hence, we only show that here. But you can find details in the paper about other policies evaluated. For evaluation, we use two-socket Cascade Lake with Intel Apache Fast DIMMs. We use these platforms and limited DRAM and SCM sizes to get different server configurations. The servers we evaluated are 1P server with 64 DRAM, 1P variants with 64 DRAM and 128 SCM, and with 32 DRAM and 128 and 256 SCM. We chose the server configurations based on available DRAM and SCM module with granularities, and the minimum DRAM required to run Linux OS and softwares. We then use the memkind library for memory allocation management. For evaluation, we created workloads based on production traces. I'm not going to go in details, but we have more details about how we generate workloads in the paper. Now let's look at our result. This is the throughput comparison of the 3 workloads we used for DRAM first policy. In the x-axis, we have the 3 server variants we used, and in the y, we have the throughput normalized to the 64.0 configuration, which is the 1P server. Here, we're talking about throughput, so higher is better. As we see in the graph, adding SCM to 1P servers with 64 gigabytes of DRAM provides 25% to 80% throughput improvement in all configuration for all workloads. And here, we show the P50 read latency in the applications. We have server configuration in the x-axis and latency in the y. We can see from the graph that P50 latency stay the same, mostly with minor variations. Except for later, we see better latency because of its relatively lower locality. And here, we have P95 and P99 latency in the y-axis and server configurations in the x. Here, lower is better because we're talking about latency. So as we can see in the graph, P95 and P99 latency are affected much more by the reduction of DRAM size. And we see an average of 20 to 10% improvement, respectively, for P95 and P99 latencies when we add SCM to 1P servers. Here's a deep dive analysis of WhatsApp for DRAM first policy. We show I/O bandwidth, cache hit rate, and I/O weight and CPU utilization. As we see in the graph, SCM increases cache hit rate up to 30%, and I/O bandwidth is reduced by 0.8 gigabytes per second. And as we see on the graph on the right, CPU utilization increases, but it's still within the 1 CPU limit. Other workloads also follow the same trends as above. We also compared performance and cost of 1P variants and 2P servers. As seen in the graph, with 1P variant, we can achieve 95% performance of 2P servers in average for our largest 1P variant, which is the 32256 configuration. We then calculated the cost of each variant using the cost of all components. Currently, SCM costs 0.38 of DRAM per gigabyte. Then based on this, for our largest 1P variant, we were able to reduce TCO to 43 to 48% of 2P server. So this TCO improvement translates to reducing number of servers and the power budget per service. Although SCM gave us good results, as shown here, it also comes with its limitation. The first one is in workloads. So we focused our analysis on read-dominated workloads, but there are also a number of write-heavy workloads at Facebook that would not benefit from SCMs. And the second is reliability. So SCMs are not widely available in the market. So the reliability of SCM is going to be a concern until they've been proven in mass deployments. And the second is SKU diversification. So adding a new hardware configuration into the fleet is going to add additional costs. Costs such as qualification costs, maintenance costs, and scale deployment costs that are not included in the TCO analysis in this paper. In conclusion, we studied the benefit of SCM using Intel Optane memory for 3 read-dominated RocksDB workloads at Facebook. We extended RocksDB to add new hybrid cache with multiple block cache that uses different kinds of memories. Then we were able to demonstrate up to 50% throughput improvement in average and 20% latency decrease by creating new 1P server variants. And finally, we would like to thank our collaborators at Facebook and at the University of Michigan for their help and feedback, and also the anonymous reviewers for their valuable comments. Thank you.